So now I'm going to look at two functions. The first one is mapping R3 to R3, and the second is mapping R2 to R4. And in the question, this is from the textbook 2.1 number 3. I believe it's B and C. So with it, just double check that. Yeah, sorry, it's B then A. So this is, the first one is B, this here is B, and this here is A. And the question is to prove whether or not these are linear transformations. And the thing that I'm going to add is if T is a linear transformation, define T alpha beta using the appropriate standard bases. Meaning that for this expression here, the standard basis would be E1, E2, this would be E1, E2, E3, E4. And we're just creating the matrix representation. Here it'd be E1, E2, E3, E1, E2, E3. First, we need to prove whether or not it's a linear transformation. And second, we need to prove if it is a linear transformation, then we need to define the matrix representation. So to prove linear transformations, we need to show that T of CV plus D, or CU plus DV equals CTV plus DT, or CTU plus DTV for all U and V in my vector space, and in my vector space V, which is the input vector space, and C and D in my field, which in this case is going to be R. So because of this, we need to pick a generic thing and try to show the left side equals the right side. And a classic way to show something isn't a linear transformation is show that T of 0 does not equal the 0 vector. And here, if we look at T of 0, 0, sorry, T of 0, 0, 0, this equals 1, 0, 0, which does not equal 0, 0, 0. Thus, T is not a linear transformation. Now, that doesn't always work. So while if you can see that, it's really nice, really easy to use, typically shows is a very fast way to show something's not a linear transformation. Not always the case. That doesn't always work. For example, you've got T of X equals X squared. This is not a linear transformation, but it maps 0 to 0. If we take a look at another approach, though, let's look at the left side and right side, but we're just going to let U and V be in R3 and C and D be in R, then U equals X1, X2, X3, and V equals, or X1, Y1, Z1, and V equals X2, Y2, Z2. Now let's look at what happens to our left side. Our left side equals T of CU plus dv, which equals t applied to cx1 plus dx2 cy1 plus dy2 cz1 plus dz2. Notice I'm expanding this vector addition inside before I apply my linear transformation. That's what my left side is going to equal. And I'm just going to rewrite this later when we get to it. And this is equal to, now I'm going to apply the function. So it's going to equal 1 plus cx1 plus dx2, 2 times cy1 plus dy2, and then cz1 minus dz2 minus cx1 plus c2. So that's my left side. My right side equals ctu plus dtb, which is equal to c times 1 plus x1 2 y1 z1 z1 minus x1 plus d 1 plus x 2 not close bracket yet, 1 plus x2 2y2 z2 minus x2. I'm going to collect these together now to get c plus d plus cx1 d plus dx2 2cy1 plus 2dy2 cz1 plus dz2 minus cx1 minus or plus dx2. And if we look at it, these two expressions are really similar. In fact, these two terms here are the same. So whole parts of it are actually the same. But we know, because the zero vector doesn't map to the zero vector, that something must be different. So what must be different is over here, this 1 plus and this c plus d. And here, this portion here is the same as this portion here. So this c plus d and this 1, that's what's different. So we need to create, because as c plus d does not always equal 1, this is not always true. That's what we want to show. That it doesn't always, left side does not always equal right side. And making the statement as c plus d does not always equal 1, this is not always true, is not the clearest way we could say it. A more clear way to say it is let c equal D equal 0. You could let C equal D equal 0, or and I'll encourage you to go through that, or we're going to do let C equals 1 and D equals 1. And now if C equals 1 and D equals 1, well, what happens? Well, then our left side here, and here we can pick x1, x2, x3 to be anything we want. So we're going to let C equals 1, D equals 1, x1 equals 0, x2 equals 0, and x3 equal 0. Then our left side equals 1 plus 0, 0, 0, and which equals 1, 0, 0. And our right side equals 1 plus 1 plus 0, 0, 0, which equals 2, 0, 0. And now, as left side does not equal right side, this equality does not hold for all x, y in R3 and C, D in R. And what I did is I looked at, could it be true? And expanded out and figured out what the left-hand side are and what the right-hand side are. Compared them, figured out where they're the same, but then I figured out where they were different. And I came up with a specific example to show that they're different. And because I could show the left-hand side doesn't equal the right-hand side for this specific example, it is not a linear transformation. Again, all you need to do is come up with an example to show it's not a linear transformation. But left-hand side equals right-hand side is typically an easy way to come up with that example. Okay. So because it's not a linear transformation, we don't have a matrix representation.